Welcome back, students. Today we are going to discuss primarily interference by division of amplitude. But before we do that, as I have done in my previous two lectures, let's have a brief recapitulation of the last class. So what did we learn from the last few classes? We have discussed till now interference by division of wavefront. We have rather completed it. And in doing so, we have discussed three arrangements, namely Young's double slit arrangement, Fresnel's biprism arrangement, and Lloyd's mirror arrangement. Young's double slit setup and Fresnel's biprism setup have same conditions for maximum intensity and minimum intensity that we have seen. And what were the conditions? The conditions were like these. When the path difference between the two waves emerging from the two sources S1, S2 was an integral multiple of lambda, we had maximum intensity and we had a bright fringe. When this path difference was an odd integral multiple of lambda by 2, we had minimum intensity or a dark fringe. Now in both these cases, that is the cases of Young's double slit setup and Fresnel's biprism setup, we had the central or zero order fringe bright, or it was of maximum intensity. For Lloyd's mirror setup, the intensity conditions were just opposite to that of Fresnel's biprism and Young's double slit. What were they? In case of Lloyd's mirror, you will remember there was one real source and one virtual source. The virtual source was created by reflecting light waves from the real source by a plane mirror. So, in case of Lloyd's mirror setup, if the path difference between the waves emerging from the two sources and superposing on the screen, if that path difference was an integral multiple of lambda, we obtained minimum intensity or a dark fringe. On the other hand, if this path difference was a half integral multiple of lambda, half integral multiple of lambda, yes, the intensity was minimum and intensity was maximum and we obtained a bright fringe. Central fringe was not obtained as such in Lloyd's mirror experiment. For that we needed to move the screen and touch the mirror, one end of the mirror, then only the central fringe could be obtained. So when the central fringe was so obtained, the zero order fringe was so obtained, we found it to be dark. Now this was rather different from the cases of Fresnel's biprism and Young's double slit. Why was this? Why was this dark? And why were the conditions different from that of Young's double slit and Fresnel's biprism? It is because the reflected ray in a Lloyd's mirror setup had an extra path length of lambda by 2 or an extra phase of pi. Now this is generally the case whenever light is reflected while traveling from rarer to denser medium. The reflected light wave has an additional path length of lambda by 2 and an additional phase of pi. The opposite is not true. That's what we had learned from Stokes' relations. So that is all as far as the brief recapitulation of the last classes are concerned. Now, we would rather move to interference by division of amplitude, and we will start with the topic of thin film. To be more precise, the reflected waves from thin film. Now, light partially reflected from upper and lower surfaces interface of a thin film having refractive index mu when mu is greater than 1 cause interference by division of amplitude. Well, that is not the only case, but this is one of the cases, the case of thin film, where we have interference by division of amplitude. Okay, so this is our thin film. The thin film here is bounded by two surfaces, AB at the top and CD at the bottom. Okay, and these two are not parallel to each other. As you see, these have an angle alpha in between them. Now P is a point source from which light ray PQ is incident on the top surface AB. After being incident, it is being reflected along QO partially, and partially it is being refracted through the thin film along the path QR. That's what happens in case of division of amplitude. Now when this QR ray is meeting the surface CD at the bottom of the thin film, it is once again experiencing reflection. It is moving along RS, and finally at S, when it is meeting the top surface AB again, it is undergoing reflection and refraction, and the refracted ray SO is meeting with the previously reflected ray QO at the point O. Now at point O we have two reflected waves, namely QO and SO superposing. We would like to know what is the intensity at the point O. Actually, there will be a path difference between the two waves that are superposing at O. Why is that? If you look at the diagram, you will see that the path difference arises because we are checking the paths QO and QRSO. So the path difference between QO and QRSO are required. For that, as you see, we have made a construction. We have dropped two perpendiculars, SN and SN1, on QO and QR respectively. Okay. Now, what we do when we drop these perpendiculars, how does it help in finding the path difference? Now see, what we need to find is basically the path QN1 plus N1R plus RS. This is the extra path traversed by the ray QRSO. Rather, we are interested in knowing the optical path than the geometric path. That's why we need to find mu into Qn1 plus N1R plus RS, and from that we need to subtract the extra path traversed by the ray QO as well, namely Qn. So the path difference between the two rays QO and QRSO is mu into the sum of Qn1 N1R RS. From that we subtract Qn. Now as you see, mu is the refractive index of the medium of the thin film, so mu is equal to sin I by sin r, and from the construction you will see the angle of incidence I and the angle of reflection at the first surface AB is also I. Now it is very easy to find out. Now it's very easy to find out that the angle NSQ will also be I. Why is that? Now if you see angle NQS in this diagram, angle NQS is pi by 2 minus I. Triangle NQS is a right angle triangle with SNQ as the right angle. So obviously angle NSQ will be angle I. Likewise, the refracted angle R. Let's check the refracted angle R. You see in this triangle SQN1, angle SQN1 is pi by 2 minus r1. And triangle SQN1 is a right angle triangle, SN1Q being the right angle. So the third angle, that is QSN1, is equal to R. So sin I by sin R, which is basically mu, is equal to the ratio of two ratios, Qn by Qs and Qn1 by Qs. Now, so what can we write? We can write Qn is equal to mQn1. Now, if I replace Qn by this relation in the path difference expression, we get the path difference is equal to, you see the first term mu Qn1 cancels out with Qn, that is the last term, and we are left with mu n1r plus rs, that is product of mu and the sum of n1r and rs. Okay. Now PQ, as I told you, is incident on AB with an angle I. QR is refracted at R. Sn and Sn are on the perpendiculars. There is nothing much new. Just I am recapitulating the constructions. Here, this is important. QR is incident at angle R minus alpha on CD. Why is that? See, QR, this refracted ray, makes an angle of refraction R. When it is incident on CD, had CD been parallel to AB, then we would have had the angle of incidence equal to R, but they are not parallel. AB and CD have an angle alpha in between them. So the angle of incidence of QR on CD would be R minus alpha. It will also be reflected along RS with the same angle R minus alpha. Now from S, a perpendicular SL is dropped on CD and extended to meet the extended segment QR at the point M. Why do we do this? It will be clear very soon. Now look at angle SRL. What is angle SRL? As you know, the ray RS is reflected by CD with a angle of reflection R minus alpha. So angle SRL will be pi by 2 minus R minus alpha. So what is the value of angle RSL? As you see, triangle SRL is a right angle triangle with angle SLR as the right angle. So angle RSL, what will it be? It will be pi minus angle SLR, that is pi minus pi by 2, and from that we would subtract angle SRL, that is pi by 2 minus R minus alpha. So what is angle RSL? It is pi minus pi by 2 minus pi by 2 minus R minus alpha. So angle RSL is R minus alpha. This is very important. You need to understand this. Okay, please check it out. So if angle RSL is equal to R minus alpha, we need to find what is the value of angle RML. Now RML is an angle inside the triangle RLM. RLM, this triangle, is also a right angle triangle with angle RLM as the right angle. So angle LRM, what would this be? If you check out, you will find angle LRM is nothing but pi minus 2 minus R minus alpha. Why 2 minus R minus alpha? Can you tell me why? Because see, angle of incidence of ray QR on surface CD is R minus alpha. The angle of reflection is R minus alpha as well. So if I subtract the angle QRS from 180 degree, I am basically subtracting twice r minus alpha from pi. So I am left with angle SRM. Okay. Now I want angle LRM. Angle LRM is what? So from SRM, I need to subtract angle SRL. What is angle SRL? Angle SRL is nothing but pi by 2 minus r minus alpha. This is what we have seen in the previous line. So angle LRM is pi minus 2 minus r minus alpha, 2 into r minus alpha minus pi by 2 minus r minus alpha. So it is pi by 2 minus r minus alpha. If angle LRM is pi by 2 minus r minus alpha, then obviously angle RML is pi minus pi by 2 minus pi by 2 minus r minus alpha. That is angle RML is also r minus alpha. So we see in triangle SRM, the angles RSL and angle RML are equal. So triangle RSM is an isosceles triangle with equal sides RS and RM. Now let's check out our path difference expression. We required mu into N1R plus RS. Now in place of RS we can replace RM. Why? Because since both are the two equal sides of an isosceles triangle. So mu N1R plus RS is mu N1R plus RM. Now if you look back at the diagram, N1R plus RM is nothing but N1M. So mu N1M is equal to mu Sm cos R minus alpha. Why is that? Now we would look at the triangle SN1M. Triangle SN1M is a right angle triangle with angle SN1M as the right angle. Okay. And angle SMN1 as R minus alpha. So what is the value of N1M? N1M would be Sm, the hypotenuse, into cos r minus alpha. That is why the path difference of the two rays we are interested in is mu Sm cos r minus alpha. If you have any confusion in understanding this, you can just replay this part of the video and find it out, or you can send me an email. The email address is given at the end of this lecture. Hence, the two reflected waves superposing at O has an optical path difference equal to twice mu t cos r minus alpha. Okay, why? Why twice mu t cos r minus alpha? We had obtained mu Sm cos r minus alpha. What is Sm? Sm is Sl plus Lm. You know, in an isosceles triangle, Sl and Lm will be equal, so we can write Sm as twice Sl. Now, twice Sl is nothing but the thickness of the film at the location S, and we have represented the thickness by the alphabet small t. So the path difference becomes 2 mu t cos r minus alpha. So two consecutive reflected rays reflected by the surface of a thin film, the top and the lower surface. These two consecutive reflected rays, when they superpose, will have a path difference of 2 mu t cos r minus alpha, when alpha is the angle between the two surfaces. That is, we are considering a thin film but whose surfaces are not parallel, they are oblique, having an angle alpha between them. So delta is equal to 2 mu t cos r minus alpha. Then conditions for Imax and Imean. You see here the ray deflected by the top surface of the thin film is basically reflection that is taking place when the ray is traveling from the rarer to the denser medium. Okay, so as we have seen in our previous classes, this ray, this reflected ray, will have an extra phase of pi or an extra path length of lambda by 2. So that is why when 2 mu t cos r minus alpha is equal to 2n1 n plus 1 lambda by 2, we have maximum intensity. When 2 mu t cos r minus alpha is an integral multiple of lambda, we have minimum intensity. So the conditions are almost similar to that of Lloyd's mirror, because there is a reflected ray. When reflection takes place while the ray is passing from a rarer to denser medium, this reflected ray will have an extra phase pi and an extra path length lambda by 2. That's what I've emphasized here. Remember, QO is reflected by the dense medium, that is mu is greater than 1, RS by the rarer medium. Yes, I haven't stressed this. Let me repeat it again. QR is incident on CD. So QR is a ray which is incident on the interface, but QR is traveling from denser to rarer medium. So RS is not going to have an extra phase of pi or an extra path length of lambda by 2. Therefore, Q will have an extra path length of lambda by 2. Hence, these are the conditions for maximum and minimum intensity for the reflected rays from a thin film. Now, the transmitted waves. I won't be going into the derivation for the transmitted waves. Just remember, in transmitted waves, you can derive it yourself. Just try it out. I'll give you some hints. I've given the diagram and the constructions. I'm going to emphasize on that. But before that, remember the path difference between two consecutive transmitted waves from a thin film is 2 mu t cos r minus 2 alpha. Previously, for the reflected rays, we saw the path difference was 2 mu t into cos r minus alpha. Here it is cos r minus 2 alpha. So we have to proceed in a similar way, just the constructions will be different. In this case, drop two perpendiculars Tn1 and Tn from T on Rs. Drop the perpendiculars Tn1. Can you see Tn1? Here Tn1 and Tn on the two rays Rs and RO1 respectively. You also drop perpendicular TL on the surface AB and extend TL so that it meets extended RS at M. Okay. Here delta is equal to 2n lambda by 2, when delta, that is the path difference, is 2n lambda by 2, that is an integral multiple of the wavelength. We have maximum intensity, and delta, when it is equal to a half integral multiple of lambda, we have minimum intensity. So we have just opposite conditions of reflected rays. Why is that? I won't tell you. You have to reason and find out. Just check whether there is any chance of having an extra phase or an extra path length of lambda by 2. If you check that, use your head and you will find out why is it this way in case of the transmitted waves. Okay, so let's move to the next topic. The next topic is interference by wedge-shaped film. We are interested in how the interference pattern will be. You know, in case of ordinary interference by division of amplitude in case of thin films, when the source is a point source, the fringes obtained will be circular. Okay, why is that? There is a detailed discussion on this in Ajoy Kumar Ghatak's book. You can go and check in it, or you can ask me. I will refer the exact pages where you'll get a good discussion on this. In case of wedge-shaped film, we are using an extended source. That's why, see, on the surface AB, we are having lot of rays coming down, 4 rays here. Okay, so what is a wedge-shaped film? You know what is a wedge-shaped film? We have just shown a wedge-shaped film of refractive index mu greater than 1, and the angle alpha is also taken as small, and this wedge-shaped film, the section of the wedge-shaped film by this display plane, that is the plane on which you are seeing this lecture, is therefore a triangle. Okay, The triangle is, you find A, B, C. Okay. Now, light wave from an extended source is made normally incident on the film. Okay. Waves reflected from the surface AB and AC give interference fringes perpendicular to this display plane. Okay. So let's say we have one fringe at P and one fringe at Q. So if we have one fringe at P and one fringe at Q, then these fringes are basically perpendicular to this display plane, that is the plane on which you are seeing this video lecture. Waves reflected by AB and AC, okay, they will superpose, and we already know that the path difference at P will be 2 mu t. You might ask, why not set 2 mu t into cos r minus alpha? No, it is not so, because as you know, the incidence is normal, okay, and that is why r equal to 0 and alpha is small. Okay, that is why the cos part is vanishing, and we have, it's not vanishing, it is becoming 1, and we have 2 mu t. When 2 mu t, this path difference is a half integral multiple of lambda, we have maximum intensity, and when this path difference 2 mu t is an integral multiple of lambda, we have minimum intensity. Why is that? Once again, see, when the light is being reflected by the surface AB, light rays are traveling from rarer to denser medium. So light reflected by the top surface will have an extra path length of lambda by 2, whereas light reflected by the bottom surface, namely AC, won't have this lambda by 2. Why? Because when it is being reflected by AC, the light rays are traveling from a denser to a rarer medium. Let the length AP be xm and AQ be xm plus 1, and AP, that is the point P and Q, are locations of two consecutive bright fringes. So this is the situation. Let us consider this situation when P and Q are the locations of two consecutive bright fringes. We know that by simple rule of geometry, we will have T is equal to xm into alpha, okay, and what will we have? We will also have, that is basically angle is equal to arc by radius, so alpha is equal to T by xm, and also it can be written as T by xm plus 1, where we have taken the thickness of the film at both locations P and Q as T. Why can we take that? Because the distance of P and Q is not much. So what do we have? We have, replacing T in the path difference formula, we have 2 mu x m plus 1 alpha, 2 mu x m plus 1 alpha is equal to twice m plus 1 lambda by 2, and 2 mu x m into alpha is equal to 2m plus 1 lambda by 2. So this is because of the mth and m plus 1th ordered bright fringe. We have written the path difference is equal to 2m plus 3 lambda by 2 and 2m plus 1 lambda by 2. So what is the fringe width? The fringe width is the difference of xm plus 1 and xm. It is equal to lambda by twice mu alpha. See, fringe width will be directly proportional to the wavelength of light. So if we are using larger wavelengths, we are going to have wider fringes. It is inversely proportional to refractive index. If the refractive index of the material of the wedge-shaped film decreases, we are going to have wider fringes. If the angle is large, we are once again going to have, if the angle is small, we are going to have wider fringes. If the angle is large, we are going to have smaller or thinner fringes. Okay. So we see that all these fringes are linear, and these fringes have uniform fringe width. So that's the end of the wedge-shaped film interference topic. Now, the most interesting part of interference by division of amplitude, namely interference by Newton's rings. So this is the arrangement of the Newton's rings. You can see the diagram is given. Okay, light from an extended source. What is the extended source? S is partially reflected by G and made incident on the combination of plano-convex lens AOB and plane glass plate POQ. O is the point where this plano-convex lens AOB and PQ are touching each other. Now, the fun of this partially reflected plate is that whatever light is incident on it, it will let half of it pass through it and half of it get reflected. That is why it's called partially reflected. It is nothing very strange. You also see it may not be 50%, but general normal window glass panes often do that. You stand in front of a window glass pane, you will see your reflection, whereas you will also be able to see the other side of the window pane. Light waves reflected by the binding surfaces AOB and POQ of the air film give an interference pattern visible through microscope M. Remember, in Newton's ring arrangement, we basically are using one plano-convex lens and one plain glass plate. In using these two, we are not making any glass film. We are rather making an air film, and it is a peculiar shape bounded by the surfaces AOB and POQ. You see AOB and POQ bounded by the surface. A air film is formed and interference rings are formed in it, and we can see it by the microscope at the top M. Interference pattern consists of alternate dark and bright rings with a dark central spot. If AOB and POQ are perfectly touching in each other, we will have a dark central spot. Okay. Now, interference due to reflected wave, we know it is 2 mu t cos r minus alpha. Now, we are having here near normal incidence. So, r will be 0. And since lens is of large radius of curvature, we can have alpha is also equal to, we can say alpha tends to 0 as well. So the path difference is no more 2 mu t cos r minus alpha, it reduces to 2 mu t, when t is the thickness of the air film at a particular location, or the location where we are trying to find what will be the brightness of the ring. Now, obviously, you see when the rays are reflected by the surface AOB, light is traveling from denser to rarer medium. Whereas when it is reflected by the surface POQ, light is traversing from rarer to denser medium. So when both these reflected waves move up and superpose on each other and we see them by the microscope, this is a case where the reflected ray by the surface POQ will have an extra phase of pi and an extra path length of lambda. So the conditions for maximum intensity will be 2 mu t is equal to half integral multiple of lambda, and that of minimum intensity will be 2 mu t when 2 mu t is equal to an integral multiple of lambda. That's what I said. Wave reflected by plane mirror has an extra path length of lambda by 2. That's why these are the relations. Now, there can be another case. This is for reflected rays, the type of Newton's rings we will see. Now, for transmitted rays. For transmitted rays, we just place the microscope on the side of PQ, not on the side of G. See, you have placed the microscope here. Now, here the rays will be coming interference due to transmitted waves, so we will have delta is equal to 2 mu t cos r minus 2 alpha. But yes, r is tending to 0 here because near normal incidence, and capital R, that is the radius of curvature of the lens, plano-convex lens AOB, or more precisely the surface AOB has a radius of curvature very large. We can say alpha also tends to 0, so the path difference becomes 2 mu t when t is the thickness of the air film at a particular location. But here the condition of maximum intensity will be maximum minimum intensity will just be opposite as we had it for the reflected wave. Here, when 2 mu t is equal to an integral multiple of lambda, we will have maximum intensity, whereas when 2 mu t is an half integral multiple of lambda, we will have minimum intensity. Can you tell me why? I leave it to you as an exercise. Find it out. Use your head and you will know why. See, these beautiful rings are obtained. On the left, we have Newton's rings due to reflected waves. You see the central spot is dark. And on the right, we have Newton's rings due to transmitted waves, and the central spot is bright. Okay, now we will try to find out the diameter, the expression for diameter of the Newton's rings, or the expression of the wavelength of Newton's rings that can be determined. And we will also try to find the expression for radius. Radius of a curvature of the surface AOB, that is OC, is R. So OC here is R. Yes, this is OC, this is R. Radius of a ring corresponding to the thickness of the air film T at M here. This is the thickness of the air film T at M. That's the radius of the ring. Whatever ring is formed at T, or rather at M, the radius is OO prime. And we are naming the radius as rho m because we are saying it is a mth order ring that is formed at M. Since EO is equal to 2R, you see, EO is 2R. Why? Because OC is R. EN will be EN, this length. This length will be 2R minus T. Because why? Because NO is T. NO is same as MO, MO prime, that is why it is T. So En will be 2R minus T. And from geometry we know OO prime into OO prime is equal to, that is OO prime into OO prime is equal to En into NO. Okay, so what is OO prime into OO prime? It's simply rho m square, and En we have written it as 2R minus T. I told you why. You can just see from the diagram. And NO is nothing but T. So rho m square is equal to 2RT minus T square. We can neglect T square because T is very, very less than capital R. So rho m square is equal to 2 capital R small t. So what is 2t? 2t is equal to rho m square by R. Why we are interested in knowing the value of 2t? Because you know, if we had a case of normal incidence and the film had a thickness t, the path difference is 2 mu t. Since in this case the material of the film is air, its refractive index mu is 1, so that is the path difference becomes twice t. So that's why we are trying to find the expression, the equation or the value of 2t. It is 2t is rho m square by R. Now, if at the point M we have mth order bright ring, then 2 mu t will be equal to 2m plus 1 lambda by 2. I am not going to emphasize once again why. You know by now why. And we have then just replace 2t by rho m square by R. You have mu into rho m square by R. That becomes equal to 2m plus 1 lambda by 2. So rho m square is equal to 2m plus 1 into lambda R by twice mu. So what is dm? Dm is the diameter of the mth order bright ring. In this case, dm is 4 times rho m square. So dm square is equal to 4 times 2m plus 1 lambda capital R by 2 mu. For the m plus pth order, say m is 5, m plus and p is 15, or let's say p is 10. So if m is 5, m plus p will be 15. So for if we have the m plus for the m plus pth order bright ring, at what we will have? We will have 2 mu t is equal to twice m plus p plus 1 lambda by 2. And finally we have d square. You can just do this calculation by yourself. D square m plus p is equal to 4 times 2 into m plus p plus 1 lambda r by 2 mu. Now for bright rings, what we will have for bright rings? You can see here we did it for bright rings only, the mth order bright ring and m plus pth order bright ring. So for bright rings we have, sorry, yes, the difference of the diameter squares is 4p lambda r by mu, or lambda, that is the wavelength of light, is equal to mu into dm plus p square minus dm square divided by 4pr. So if we can find the diameters dm plus p and dm by experiment, we are supplied by the value of radius of curvature. It is very easy to find the wavelength of light being used for the experiment. For dark rings, what will happen? Well, these are the things that will happen for dark rings. We have the radii for dark rings, the radii of the mth order dark ring and the radii of the m plus pth order dark ring, rather the radii squares and the diameter squares also we have written. What is to be seen is, you can do the calculation yourself. Even for dark rings, the difference of the diameter squares is the same, that is 4p lambda capital R by mu, so that from the dark rings also we can find the wavelength. The wavelength expression is the same as above. Here I have written mu. Actually for air, mu will be 1, so you can just throw away the mu from the expressions. Using either bright or dark rings and above boxed expression, what can we find out? One may determine the wavelength of light of the wavelength of lambda of light used. Now if we have p is equal to 1, what we have, if p is 1, then d square m plus 1 minus dm square becomes 4 lambda capital R by mu, and we are applying some algebraic rules. So finally what do we have? We have dm plus minus dm is equal to 4 lambda mu capital R by mu into twice dm. Now capital Dm is almost taken as capital Dm plus 1. For large values of m, you know that there is not much difference of the diameter of the rings. We can see when we look at the expression for the radius of the rings. So what is the ring width? The ring width beta is lambda r by mu dm. So we see if there is an increase in m, as I was just telling you, there is decrease of beta. So you go to higher order rings, dm will be larger and we are going to have beta smaller. Now what happens? Now this is the last topic, so that ends our discussion on Newton's ring. Now we are going to a special case when in Newton's ring arrangement the lens is gradually lifted up. What will happen? So we are having a Newton's ring arrangement, and let's say the wavelength of light being used is 6400 angstroms. A plano-convex lens is being used. The plano-convex lens that was here AOB. So the plano-convex lens used here has a radius of curvature 100 centimeters, rather large, and mu, that is the refractive index of air, is obviously 1. What happens when the lens is lifted from the plane glass plate? What will happen? Let's see. So this is the initial diagram. Let's look at the diagram. This is our lens. This is our lens, and we have denoted 3 points in the lens PQR. The corresponding points in the plane glass plate is A, B, C. You see PA is equal to lambda by 2, QB is equal to lambda, and RC is equal to 3 lambda by 2. These are all relevant. We will come to these. Initially, there is perfect contact. So perfect contact between the plane glass plate and the plano-convex lens. So what happens when there is perfect contact? We will have a central spot, and the central spot will be obviously dark. Okay, now please excuse me for a moment. One second please. Yes. So for mth order dark ring, we know what is there for mth order dark ring. For any dark ring, and when the refractive index mu is 1, we have 2 mu is equal to 2m lambda by 2. So for mth order dark ring, we have 2t is equal to 2m lambda by 2. And rho m square is equal to 2m lambda r by 2. This we have done previously. So rho m is equal to root over m lambda r. Okay. Here, when m is equal to 1, that is the first dark ring, we have the thickness T dark 1 is equal to lambda by 2. That means for the first dark ring, we just need the thickness of the air film to be lambda by 2. Then in that case, twice the thickness becomes lambda, and we have the first dark ring. Here you see in the diagram, PA is that thickness, that is lambda by 2. So at location A, we are going to have the first dark ring. Now, what will be the radius of this first dark ring? It will be rho 1, that is the length OA. In the diagram, if you see, it will be the length OA, that is equal to root over lambda by r. It will be 0.80 centimeters. Likewise, for the second, that is m equal to 2 dark ring, what we will have? We will have the thickness corresponding to the second dark ring as lambda. We need that, and that's why twice of that will be twice lambda, and we see in the diagram QB is that particular thickness. So at the location B, we are going to have the second order dark ring, and what will be the radius of the second order dark ring? It will be equal to OB, and that will be root over 2 lambda r, and that will be, the value will be 0.113 centimeters. Well, so 0.080 centimeters and 0.113 centimeters are the radii of the first and second dark ring respectively when the lens is on the plate or there is perfect contact. Now, the same thing, we are using the previous result when the lens is in perfect contact with the plane glass plate. The first order and the second order dark ring were obtained at 0.080 centimeters, and when the lens was in perfect contact, the central spot was dark. Now we are lifting the lens. See, the lens is lifted by an amount OJ, and you see OJ is equal to lambda by 4. Here we have OJ is equal to lambda by 4. We are again having 3 locations. By now you can guess A1, B1 and C1 will be the new locations of the 3 dark rings. So P1 A1 is lambda by 2, Q1 B1 is lambda, and R1 C1 is 3 lambda by 2. Okay. Okay. Lens has been lifted by lambda by 4. So if the lens is lifted by lambda by 4, what is the value of T at the central spot? It is lambda by 4. Hence 2T will be lambda by 2. And that corresponds to, yes, you're right, that corresponds to maximum intensity. So central spot becomes bright. Okay. Now for mth order dark ring, what do we need? We need twice T. This twice T has to be 2m lambda by 2. Okay. So where do we get that? And we know for mth order dark ring, this is just the previous things I am doing. Rho m will be root over m lambda r. Here, when the lens has been lifted by lambda by 4, the first dark ring is obtained at P1 A1, and the corresponding radius will be, let's find out. This is something interesting. It will be 0.0566 centimeters. Earlier, when the lens was touching perfectly the lower glass plate, the first dark ring was obtained at, where was it obtained? Here, 0.080 centimeter. You see, evidently, the radius of the first order dark ring has reduced. Let's check whether the result is same for the second order dark ring. Yes, let's do it. The second order dark ring will be obtained at B1, and Q1 B1 is the required length for which we will have the second order dark ring. It will be lambda. What is the radius? It is 0.098 centimeter. You just put the values, you can find out. There is no big deal. So once again, you see the second order dark ring's radius has once again reduced from 0.113 centimeter when the lens was perfectly touching the surface of the plain glass plate. It was 113 centimeter, now it becomes 0.098 centimeter. So what is the conclusion? The conclusion is simple, and also you'll remember that when the lens was lifted by lambda by 4 amount, the central spot turned bright. So it appears as if the rings are converging towards the central spot, and one by one they are falling into the central spot. That's why the color of the central spot is changing. When the lens was perfectly touching the plain glass plate, the central spot was dark. But when we started lifting it and we reached the height lambda by 4, that means the lowermost point of the lens is at a height lambda by 4 from the surface of the glass plate, then only we see suddenly the dark central spot turns bright, as if the very adjacent bright ring falls into the dark spot, and the dark rings one by one are closing towards the central spot. That is why lifting of lens causes the rings to collapse to the center. So that ends today's lecture. We have basically discussed interference by division of amplitude. We started with a rather general case when light used was a point source. Thin film was used whose surfaces were not parallel. We found the conditions of maximum intensity and minimum intensity both were reflected, and it was discussed what will be the condition when the rays are transmitted. We found the conditions, then we found out what will be the fringe width for a wedge-shaped film. Finally, we dealt with Newton's ring. We found the radius, we derived the formula of radius and diameters of Newton's rings, and from that we derived an expression with the help of which we can find out the wavelength of the light being used to produce Newton's ring. And finally, we discussed this particular case, what happens when the lens is lifted in a Newton's ring arrangement. We found that one by one the rings start collapsing. So that's the end of my lecture, the third video lecture. So thank you, and for clarifications, clearing of doubts, you can write an email to edudipgu@gmail.com or edudipgo@gmail.com. Bye bye.